Hello friends, I, Dhairya Bhatia, welcome you to my YouTube channel Maths DNA from origin to infinity. In this video, we are going to solve the questions of linear algebra asked in GATE 2019 Mathematics. But before that, let me share something with you. If you are looking for more questions, material, test series and previous year papers as well, then you can visit my Telegram channel and the link is given below in the description. So let us begin with the questions. The first question we have, let V be a vector space of all 3 cross 3 matrices with complex entries over the real field. If W1 equals to A belongs to V such that A equals to A conjugate transpose and W2 equals to A belongs to V such that trace of A equals to 0, then the dimension of W1 plus W2 is. This question is already discussed in one of my videos, but here I thought covering all the questions of linear algebra would be a good one. So let us solve this question. Firstly, we find A. Now what is A? A is a matrix whose entries are complex where A11 plus IB11, A12 plus IB12 up to A33 plus IB33, a 3 cross 3 matrix, and Aij and Bij belongs to R, that is set of real numbers. Now it is already given to us that A belongs to V, and here the dimension of V is 18. Why 18? Because it is a 3 cross 3 matrix, but the entries are complex, so it will be 2 times of 3 cross 3, that will be 18. Now, W1 is nothing but A belongs to V such that A equals to A conjugate transpose. We already have the matrix A. Now we find A conjugate transpose. It will look something like this, where the sign of the complex entry, that is I, is changed and the rows are converted to the columns, that is A11 minus IB11, A21 minus IB21 up to A33 minus IB33. Now in W1 we have A equals to A conjugate transpose. So putting both the matrices as equal and then equating them term by term. Firstly we get A11 plus IB11 equals to A11 minus IB11, which implies that A11 gets cancelled out and 2IB11 equals to 0, and which implies B11 equals to 0. Similarly, you can solve the second element and the third element, and this will give you B22 equals to B33, which is equals to 0. So the entries with the imaginary part on the trace becomes 0. Now comparing the other entries, that is second entry, A12 plus IB12 equals to A21 minus IB21. Now here we get A12 equals to A21 and B12 equals to minus B21. We are comparing just real and the imaginary part. In general, you can say it as Aij equals to Aji and Bij will be equals to minus Bji, and so you get our required A, that is the entries on the diagonal are A11, A22 and A33, because B11, B22 and B33 we already proved them 0, and the above diagonal entries we get them as A12 plus IB12, A13 plus IB13 and A23 plus IB23. Below the diagonal the entries are same, just there is a change of sign in the entry in the complex number, and so we get dimension of W1 as 9. Please note it down. Moving on, W2. W2 is a matrix, is a set where A belongs to V such that trace of A equals to 0. Now we already have our A, and here they are saying the trace of A equals to 0. So that is A11 plus A22 plus A33 should be equals to 0, which implies that any one element is dependent. You could say A11 equals to minus A22 minus A33, which simply means that A11 is dependent on A22 and A33. Similarly, for B11 plus B22 plus B33, any one of the element will be dependent. So we found two elements to be dependent, and this gives us dimension of W2, that is 18 minus 2, and that is equals to 16. So we already have the dimension of W1 and we already have the dimension of W2. Now we find the dimension of their intersection. Do not forget to find the dimension of their intersection. Now the dimension of their intersection will be 9 minus 1, that is equals to 8. Now how do we get this 1? This 1 is a common element which is present in both on the trace, that is, suppose A11 we take it as minus A22 minus A33. Then from here we get W1 intersection W2, a matrix where the entries are minus A22 minus A33, and again A22 on the diagonal A33, and the above the diagonal entries are same, and here the dimension of W1 intersection W2 will be 8. So we found all the required terms. Now simply finding dimension of W1 plus W2, that will be equals to dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. We have all the entries and the numbers, so dimension of W1 plus W2 will be equals to 9 plus 16 minus 8, and that will be 17, and hence the correct answer is 17. Moving on to the second question. Now this question seems to be a lengthy one, but is a simple one if you know how to solve it. Now let P2 be the vector space of all polynomials of degree at most 2 over R, that is the set of real numbers. Let a linear transformation T from P2 to P2 defined by T of A plus Bx plus Cx square equals to A plus B plus B minus C into X plus A plus C into X square. Then consider the following statements. The null space of T is alpha into minus 1 plus X square for alpha belongs to R. Second, the range space of T is spanned by the set 1 plus X square and 1 plus X. The third one, T of 1 plus X equals to 1 plus X square. And the fourth is, if M is the matrix representation of T with respect to the standard basis 1x and x square of P2, then the trace of matrix M is 3. We have to find which of the following statements are true. The options are A 1 and 2, B 1, 3 and 4, C 1, 2 and 4, and option D 2 and 4. Firstly, we will write down what is given to us, and then we will solve each and every statement step by step. It is given to us that T is a linear transformation from P2 to P2, and that defined as T of A plus Bx plus Cx square equals to A plus B plus B minus C into X plus A plus C into X square. This is to be noted down, and now let us solve the question with each and every statement step by step. The first statement says that the null space of T is alpha into minus 1 plus X square for alpha belongs to R. We all know what is a null space. Null space is just linear transformation mapped on 0. So here the transformation is T of A plus Bx plus Cx square, and we map it on 0. This gives us A plus B plus B minus C into X plus A plus C into X square equals to 0 plus 0x plus 0x square. For the convenience, I have written 3 times 0 so that you can compare each and every term on the left hand side to the right hand side with the coefficients. So we get A plus B equals to 0, B minus C equals to 0, and A plus C equals to 0. On solving these 3 equations, that is very simple, we get A equals to minus B equals to minus C, and this gives our transformation that A minus AX square for all A belongs to R. B and C are replaced by minus A. Now taking minus A common from here, we get alpha into minus 1 plus X square, where alpha is nothing but minus A. So the first statement is correct, that the null space of T is alpha into minus 1 plus X square. Many students make a mistake over here. They see that the common term is A, so the null space should be 1 minus X and minus X square. But according to option, you need to go, and if you are taking minus A as common, it is also valid. So the first statement is correct once again. Moving on to the second one. The range space of T is spanned by the set 1 plus X square and 1 plus X. So we know the range space of T is nothing but the linear transformation defined for A, B and C belonging to R. So for A plus B minus C into X and plus A plus C into X square, for ABC belongs to R, we simply open up the brackets first. That gives us A plus B plus bx minus cx plus ax square plus cx square for A, B and C belonging to R. Now taking the terms with A, B and C together, we get 1 plus x square into A plus 1 plus x into B. Now the terms of CR minus CX plus CX square. From these two terms, we cannot find 1 plus x or 1 plus x square as a common element to span it. So we add and subtract C to make it a solvable. And here we get 1 plus x square into A plus 1 plus x into B. Taking minus C as common, we get 1 plus x, and plus C as common, we get 1 plus x square for A, B and C belonging to R. Here you can clearly see that the whole set is spanned by 1 plus x and 1 plus x square. So the second statement is correct as well. Moving on to the third one. The third one says t of 1 plus x equals to 1 plus x square. You need to simply apply the transformation. When you apply it for the first time, you get t of 2 plus x square. When you again apply it, you get t of 2 plus x square equals to 3 plus 3x square, and which is not equals to 1 plus x square. So the third statement is not correct. And the fourth one, if M is the matrix representation of T with respect to the standard basis 1 x square of P2, then the trace of the matrix M is 3. Firstly, we need to find the matrix. It is given to us that the transformation is T of A plus Bx plus Cx square equals to A plus B plus B minus C and plus A plus C into x square. We apply it to the standard basis. T of 1, it will be 1 plus x square, and that is equals to 1 plus 0x plus 1x square. T of x, that will be equals to 1 plus x, and that is 1 plus 1x plus 0x square. And T of x square, that will be equals to minus x plus x square, and that is equals to 0 minus 1x plus x square or 1x square. And this gives us our matrix with the entries as 1 0 1 1 1 0 and 0 minus 1 1. And here clearly the trace is 3. So the fourth statement is correct as well, and the correct answer becomes option C. 1, 2 and 4 are true statements. Moving on to the third question. This one is also a lengthy one, but again a simple one. Let M be a 3 cross 3 real symmetric matrix with eigenvalues 0, 2 and A with the respective eigenvectors U, that is equals to 4 B C transpose, V minus 1 2 0 transpose, and W equals to 1 1 1 transpose. Then consider the following statements. The first one, A plus B minus C equals to 0. Second, the vector x equals to 0, 3 by 2, 1 by 2 transpose satisfies mx equals to v plus w. The third one, for any d belonging to span of u, v and w, mx equals to d as a solution. And the fourth one, the trace of the matrix m square plus 2m is 8. And which of the following statements are correct? The options are A 1, 2 and 3, B 1 and 2, C 2 and 4, and option D 3 and 4. Let us solve this question. But before that, we need to go through some results. Firstly, it is given to us that M is a real symmetric matrix with eigenvalues 0, 2 and A, and the eigenvectors are u, v and w respectively. The result is, for a symmetric matrix, eigenvectors are orthogonal to each other, and if they are not orthogonal to each other, then they have the same eigenvalue. Now this result will be very useful. Let us begin. The first statement says A plus B minus C equals to 10. Applying the result, we take u and v should be equals to 0 because they should be orthogonal, and when we multiply it, we get minus 4 plus 2b plus 0 equals to 0. Now on solving it, we get 2b equals to 4, and which implies b equals to 2. So we found the value of b. Moving on, v over w should also be equals to 0. We have both the value of v and w. This gives us minus 1 plus 2 plus 0, and that is equals to 1 and not equals to 0, which means that V and W are not orthogonal. Now if V and W are not orthogonal, it means that 2 is a repeated eigenvalue, and thus A, that is the remaining term we have to find, is also 2. Now the last one, W over V, that should also be equals to 0, that is 4 plus B plus C should be equals to 0. We already have the value of B, that is 2, so 4 plus 2 is 6, 6 plus C equals to 0, and this gives you the value of C, that is C equals to minus 6. Now when we have the value of A, B and C, we simply substitute them in the above given equation, and that gives you your required answer, that is A plus B minus C equals to 2 plus 2 plus 6, that is equals to 10, and the first statement is correct. Moving on to the second one, the vector x equals to 0, 3 by 2, 1 by 2 transpose satisfies mx equals to v plus w. Firstly, we find v plus w, that will give you minus 1 plus 1, 2 plus 1 and 1 plus 0, and that is equals to 0, 3 and 1. Now we have mx, that is m into 0, 3 by 2, 1 by 2 should be equals to v plus w, and that is 0, 3 and 1. Now breaking the vector 0, 3, 1 in two parts, we get mx equals to 0, 3 by 2, 1 by 2 plus 0, 3 by 2, 1 by 2, and that is equals to 2 times 0, 3 by 2 and 1 by 2. Now we know that mx should be equals to lambda x, so we write it as m into v equals to 2v and m into w equals to 2w, where v and w are just two given vectors. Now adding left side of mv and mw to the right side of 2v and 2w, we get m of v plus w equals to 2 times v plus w. Taking 2 on the left hand side, we get m by 2 into v plus w equals to v plus w. Now v plus w, we already have its value, that is 0, 3 and 1, and dividing it by 2, we get m into 0, 3 by 2 and 1 by 2 equals to v plus w. On right hand side is 0, 3 and 1. So it satisfies mx equals to v plus w, and hence the second statement is correct as well. Now the third one, for any d belonging to span of u, v and w, mx equals to d has a solution. Now for mx equals to d and d should not be equals to 0, we have that rank of m equals to 2, and so if we apply it, we get a augmented matrix with a1, a2, a3, a4, a5, a6, and the last row is 0. And for this matrix, we get no solution, whereas the third statement says mx equals to d has a solution, which is not correct. Now the fourth one, the trace of the matrix m square plus 2m is 8. Now this was a very simple statement if you just knew a property that of matrix and their eigenvalues. Now eigenvalues of m square plus 2m will be, if 0 is an eigenvalue of m, then 0 square plus 2 into 0 will be eigenvalue of m square plus 2m. Similarly, for 1, 2, that is 2 square plus 2 into 2, that is equals to 8. And for the other two as well, 2 equals to 2 square plus 2 into 2, and that is again 8. Many students make a mistake over here as well. They just calculate the value only for single 2. But remember, in m, 2 is repeated 2 times. 2 is eigenvalue 2 times. So for m square plus 2m also, you need to find the value of 2 times, and that gives you 8 and 8 again. And now when you take the trace, it will be 0 plus 8 plus 8, and that is equals to 16. And so fourth statement is not true, and hence we get the answer as option B, 1 and 2. The first and the second statement are correct. Moving on to the fourth one, the last one. If the characteristic polynomial and the minimal polynomial of a square matrix A are lambda minus 1, lambda plus 1 raised to 4, and lambda minus 2 raised to 5, and lambda minus 1, lambda plus 1, lambda minus 2 respectively, then the rank of the matrix A plus I is, where I is the identity matrix of appropriate order. Firstly, we need to know that A is diagonalizable if its minimal polynomial is product of distinct linear monic factors. Here we have minimal polynomial as lambda minus 1 into lambda plus 1 into lambda minus 2, which is clearly distinct and has linear monic factors, and that gives you that we can find a P such that determinant of P is non-zero, that is P is invertible, and A equals to P inverse D P. Now here D is nothing but a diagonal matrix whose entries are same as the eigenvalues of A, that is 1, minus 1, minus 1, minus 1, minus 1 4 times, and 2 the remaining 5 times. Now we have to find A plus I's rank, so it will be P inverse dP plus I. We will find it first, and that will give you P of A plus I equals to P of D plus I. On solving it, we get P into D plus I will be diagonal matrix with entries 2, 0 4 times and 3 5 times. Here we have 4 zeros, so 4 will be removed from the 10 cross 10, and we will find the rank of A plus I equals to 6, and hence the correct answer is 6. Thank you, and you can be a member of our social club and watch 190 plus videos on our YouTube channel and get a complete study material on our Telegram channel as well.